Hey friends. Okay, so now we're going to start part 3 of our epic journey together. Part 3 is going to deal with kind of 2 units, exponents and logs, as well as set theory. Now, just like part 2, I've divided part 3 into 3 separate sections, so there'll be 3 different videos. Okay, the first video is going to be video 8, which we're about to do right now, and that's on exponential and logarithmic functions. Then we're going to do a video on log laws and applications, exponential and logarithmic applications. And then the third video will be on set theory. Okay, so for right now, we're going to get started on exponential and logarithmic functions. So let's get a picture in mind first. An exponential function is a function that exists in the form y equals ab to the x. Okay, now things you need to know about those parameters. A is your y-intercept, and when we get into applications, that's also your initial value. Okay, so if a starting population or maybe we're talking about like the half-life of something, and so we could say that it starts at 100%, or we could say it starts at 65 grams, something like that. But whatever it starts at, that's your A value, okay? If B is greater than 1, so if your rate here is greater than 1, it's a growth function. So it would look like the blue graph I've shown you here. And then if B is a fraction, if it's between 0 and 1, it's a decay function, okay? So that would be the red graph that I'm showing you here. Okay, so the blue graph is a growing graph, and the red graph is a decaying graph. Okay. Okay, so the rate of growth or decay can be found by using the expression b minus 1. Okay, so you take whatever your b value is and you subtract 1. If that answer is positive, that indicates growth. Okay, and if that answer is negative, it indicates decay. Okay, so say your, I don't know, say your b value was, let's write y equals 5, 1.03. Okay, so your b value there is 1.03. If I follow that formula and I go 1 point, or sorry, 1 point, did I ever do a bad job of that? 1.03 minus 1 equals 0.03. So that would represent a 3% growth. Okay, 3% growth. Okay, now let's look at it the other way. What if I had a b value of, let's say, I don't know, 0.8, okay? If I followed that same setup and I went, okay, 0.8 minus 1, that's going to equal negative 0.2, okay? That represents a 20% decay, a 20% decay, okay? Okay, now the standard domain of all exponential graphs are all the values of x such that x is a member of the reals. The standard range is y is greater than 0. Be careful with this guy because don't put equals there. Okay, it'd be y is greater than 0. And the reason you can't put equals there is because there's actually a horizontal asymptote on the line y equals 0. And so, whoops, that's why we don't put the equal sign there. Okay, so horizontal asymptote also at y equals 0. Okay, now a logarithmic function. These are the other kind of 2 pictures that you need to have in your mind. A logarithmic function is a function that exists in the form y equals log base b of x. Logs are useful when trying to get rid of a variable locked inside an exponent. Now, before we go any further, I want you to understand what you're looking at, okay? This thing here, although my computer-generated picture looks like it actually starts there, it does not. This x equals 0 is a vertical asymptote, and so this actually goes down forever, riding towards that asymptote. Okay, so if you were to ever draw them, you want to understand that that's going to go on forever. And likewise, the other guy as well. Just going to try and match my color as best I can here. This would go up forever, riding along that asymptote. Okay, so be careful that you can interpret the picture your graphing calculator is showing you. Okay, okay, so if b is greater than 1, it is a growth function. And again, that would look like the blue guy here. And if b is a fraction, that would be a decay function. And again, that would look like the red guy. Okay, standard domain is actually now x is greater than 0. because of that vertical asymptote that I was just talking about. And then the standard range is y is a member of the reals. And then you have a vertical asymptote at x equals 0. Okay? Awesome. Okay, so regression will be used on both exponential and logarithmic, sorry. Again, follow those steps that I've outlined in book 1, page 46. Take note that for log regression, we use the natural log. So your equation is going to have ln in it. Ln is log base e, where e is an irrational number called Euler's number. Okay. When you do the regression, though, it'll come out as ln. So you really just have to know how to do the regression and then answer questions on your calculator, just like you've done with quadratic regression and cubic regression and linear regression and sinusoidal regression. We're just adding in now natural log regression and exponential regression. Okay, the steps are all the same. It's just a matter of when you go, if you're Casio, when you go to calculate, you choose the right option there. And if you're TI, when you go stat calc, you just choose the right option there, okay? Okay, so identify the equation to the right. Okay, so these are all exponential equations. So things I want you to be comfortable with is, first of all, I'm comparing a starting value of 12 versus a starting value of 4. We said that that A value would be your y-intercept. So if I look at my y-intercept here, it's not 4, it has to be that 12. So that's going to rule out C and D right away. Okay, the next thing you want to ask yourself is this a growing graph or is this a decaying graph? Well, this is growing. When I'm reading from left to right, it's going up, so it's growing. Which one of these B values would give me a growing graph? Well, that's going to have to be the 1.3. So my answer would be A. Okay. Okay, the value of a particular painting increases exponentially over time. Which of the graphs below model the value of the painting V over time T? Well, it increases exponentially. So right away, I would want you to be comfortable to say this, sorry, I was just trying to change my color here. Okay, this guy doesn't work because that's a linear increase. This guy doesn't work because that's a linear increase, okay? Now, so we're forced to look at A and C. Now, what's the difference between A and C? A has a starting value of 0 and C has a starting value of not 0. Well, I can't really start at 0 and increase exponentially, right? Because I would keep multiplying things by 0 and that would still just be 0. Granted, if it was my painting, the starting value would probably be 0, but we're assuming that the starting value is something here. And so that's why we're going to have to say the answer is C, okay? C. Okay, good job. All right, the estimated value of a particular vehicle over the last 4 years of its life are given in the table below. These data can be modeled by the exponential regression in the form y equals a times b to the x, where x is the age of the vehicle and y is the estimated value. To the nearest percent, the average annual rate of depreciation of a vehicle during its first 4 years is. Okay, so we haven't done a regression in actually a couple videos. So I'm gonna do one more with you. I'm gonna throw my calculator up and we'll talk here. So just give me 1 sec to switch to my calculator. Okay, and again, we gotta put this in our list. So if you're a TI kid, you're gonna go stat edit. If you're a Casio kid, you're gonna go into stats, okay? And you're gonna put in that table. So we had 0 to 4, which I actually already have here. I just have to delete my 5, okay? And then in list 2, you put your Y value. So we've got 22,400, 19,330, 16,682, 14,397, and 12,425. Okay, just make sure you match up and that you don't have any extra data points there. Okay, so now on a Casio, we're going to press graph 1 so that we see the picture, and then we're going to calculate. Okay, you were told to do an exponential. So exponential, you got to go to more options here, and you're going to choose exponential EXP. That's F3 here. Okay. And we want it as AB to the X, so we'll choose F2 there. Okay, and again, for Casio kids, you're gonna copy and hit enter, and that will put it into Y1 for you. Okay, now TI kids, after you have your lists in there, you're gonna go stat, and then you're gonna right click over to edit, and you are going to find on your list the one that says EXP REG. Okay, and that I think for most of you, I'm just looking it up on my TI right now, is option 0, okay? EXP REG. And then before you hit enter, if you have an older TI, make sure that you go put Y1 beside it so that it will go right into Y1 for you, okay? So to do that again, you're gonna press variable and then right click over to Y variable, press 1 for function and 1 for Y1, okay? All right, now if you are a newer TI, just in that store equation section, you will type in Y1 there, okay? Now, it said to the nearest percent, the average annual rate of depreciation of the vehicle. So when I'm looking for my rate of depreciation, I am looking at this B value, which is right here. Okay, this 0.863000575. But we have to talk about that a little bit. And we have to think about the fact that it was 0.8 minus 1 gave us the rate of depreciation, right? It's the B minus 1. So we have to go 0.86 minus 1, okay? And now we're not going to answer as a negative. The negative tells us that it's depreciating, okay? But what that means is my answer is actually 14% because 0.86 minus 1 gives us 0.14. And then when I switch that to a percentage, that'd be 14%. Okay, so I'm just going to go back to the PowerPoint slide here. That was the equation that we just discovered, okay? And then we end up with that 14% as my rate of depreciation. So the value of the car is going down 14% every year is what we're saying there. Okay, all right. The population of Mathopolis on January 1st, 2015 was 50,125. The city is growing exponentially at an annual rate of 1.2%. So keyword there is growth, okay? If I'm growing, I have to be bigger than 1. So if I'm growing by 1.2%, the first thing I need to do is think about that as a decimal. That as a decimal would be 0.012, right? We just move our decimal place back because we divide by 100. But that's not going to grow. That would be like a catastrophic plague. So to grow, we need to add 1 to it, okay? So determine an equation that models the population growth since 2015. So I've got my A value here is my starting population, 50,125. And then I've got my growth rate of 1.012 to the X, okay? All right. If the growth rate remains consistent, how many people do you expect to find in the city in 10 years? So again, we go back to asking ourselves, okay, now that we're dealing with an equation, have I been given X and asked to solve for Y, or have I been given Y and asked to solve for X? Well, 10 years is my X value, and I'm asked for the final population. That's the Y value, okay? So I plug 10 in for X, and then I just type it into my calculator, and I get 56,475 people. Okay. All right. What year will the population exceed 60,000? Okay, so now, again, you're asking yourself, hey, have I been given an X or a Y? 60,000 is a Y. This time I've been given my final value, okay? And I'm asked to solve for X. So the equation I'm setting up would be 60,000 equals 50,125 times 1.012x. Okay, so now I have to solve for X. We know how to do this algebraically and we know how to do this graphically. I have divided both sides by 50.125, okay? And then I just switched it to log form. Okay, now we're gonna talk about switching it to log form a little bit more in the next section, but essentially what I need you to remember, Super easy when you remember my little mantra here. The base becomes the base. Okay, so the base of the exponent becomes the base of the log. The dude that was free is now locked into the log. And the dude that was locked as an exponent is now free. So those guys switch jobs, okay? The base becomes the base. The dude that was free becomes locked, and the dude that was locked becomes free. That's how we switch between the exponential form and the logarithmic form, okay? Now that I just type into my calculator. Very quickly, if you forget how to type that in your calculator, first of all of you can go log of 1.197. Now notice I have that ... there. That's because I'm actually not going to type that number in. I'm going to use the answer button on my calculator so I don't run into any rounding errors. Okay, so the answer button on your calculators is the second function of your negative sign. Okay, so all of you could go log of your answer divided by log of 1.012. Okay, you don't need the special log button to do this. Okay, so just for clarification, I'm going to switch over to my calculator again. And I'm just going to walk you through this real quick. Sorry, I need to just get my mouse back on too. Okay, so if I'm in my calculator, all of you have the log button right here. So you can go log of 1.197. Now, I don't actually have the number in front of me that was the non-rounded version, so mine might be a little off here, but I just want to show you what to do here. Divide by log of the base. So that would be log of 1.012. Okay, and then that's giving us 15.07. Now, if you have a special button, okay, if you have a newer Casio, you can just press math and press log AB, okay, and you can type it in that way, 1.012 and bracket, oops, get out of there, and 1.197. Okay, if you have a white Casio, you can get to the same thing by pressing option and then going to more options, numeric, and more options. Oh, sorry, let me try that one more time. It wasn't numeric, it was calc. So I apologize, I'm gonna do that one more time. Option, calc, more options, and then there's F4, the log AB. Okay, now if you're white Casio, you would have to go A comma B, okay, because it's all one line. And then if you're a newer operating system TI, you can get it by pressing math and just go up a couple and you'll see log base, it says, okay? All right, so let me just switch back to the PowerPoint. And we get 15.075. Now, that is the exact moment in time when I am 60,000, okay? Now we have to interpret the question. The question says, when will I exceed 60,000? That means I want to be greater than 60,000, okay? So what year will I exceed 60,000? Well, 15.075, that means it's gonna take 15 years and a little bit, but it's not gonna take much more, right? It's 0.75 of a year. So in what year? Well, 2015 plus 15 puts me to 2030, okay? In 2030, it'll take 15 years and then some, but 15 full years would take us to January 1st, 2030. So that then some would still happen in 2030, okay? Now, if this algebra conversation, which I think was a very good conversation to have, because I think sometimes algebra is actually easier than graphing it, but that's me. If the algebra stresses you out, now I'm going to do it on your graphing calculator instead. So we could go right back to here and we could type this in Y1 and this in Y2. You could even have divided both sides by 50,000 and done this in Y1 and this in Y2 instead if you want, okay? I chose to just take the raw one. So this is my 60,000 is my blue line, okay? And the 50,125 times 1.012 is my red line. And then I just solve for the intersection point and I still get that 15.075, okay? So especially on multiple choice questions, if you are more comfortable doing it by a graphing calculator, by all means, go for it, okay? Okay, the half-life of silver 108 is 418 years. The percentage of mass remaining, P, after T years can be modeled by the function shown below. P equals 100, 0.5 to the T over 418. The number of years it will take for a sample to decay to 65% of its mass. So again, you're asking yourself, hey, was I just given T or was I just given P? And I was actually given P, okay? That's the percentage remaining. So I'm actually being asked to plug 65 in for P here and solve for T, okay? Now, I just did that on a graphing calculator. So what I did was I put this into Y1 and this into Y2, okay? I'll do that for you if you want. Let me just switch to the graphing calculator. And we're gonna go graph. And I'm gonna have 65 in for Y1. And for Y2, I have 100 times 0.5 exponent x2 divided by 418. Okay, and I'm just looking for that intersection point. So I go to graph. I need to get a better window setting. So this is a good conversation to have as we talk about window settings. Whether you're a TI or a Casio, you have this automatic auto window setting, okay? It doesn't usually give you a good picture. I do want to walk you through how to press the buttons to get it though, because what it will do is it'll adjust your Y value, but it won't adjust your X value. So you'll still have to go and adjust your X value. But for Casio, it's zoom auto. Okay, so I just pressed F2, F5. And on a TI, it's zoom. I'm just looking it up on a TI that I have off screen here. It's zoom fit. So it's press the zoom button and then 0. Okay, so you'll notice I now see one of my lines and I see this line here, but I can see that I'm gonna have to really up my X. Okay, so I'm gonna now actually manually go to my window, maybe set my X to, I don't know, looked like it was big. So I'm gonna go 500 with a scale of 100 per second, just see what that does. Okay, that actually did exactly what I needed it to do. I can now see that intersection point. I'm going to bring my Y down a bit as well. My Y only starts at 65. I'm going to get it to start at -10, just so I can see the axis. And that's going to show me that intersection point a little better as well. Okay, so then I look for the intersection point and I get 259.78, which is where I got the 260 in the first place for that answer. Okay. Okay. So 260 years for that guy. Okay, the estimated age of a colony of bacteria in a petri dish at various population thresholds is shown in the table below. These data can be modeled by a logarithmic regression function in the form y equals a plus b ln x, where x is the population of bacteria and y is the estimated age of the colony. So again, this is just a regression question. You're going to go to stat, edit if you're a TI, and stat if you're a Casio, menu stat like. You're going to type this guy into Y or list 1, this guy into list 2. And then once you have that, you're going to perform an LN regression. Okay, so if you are a Casio, that's going to be sorry, I'm just opening it up on my, it will say log as the option on a Casio. And then on a TI, when you go stat calc, your option will say LN regression, okay? So a Casio, you'll choose the one that says log. And in a TI, you'll choose the one that says LN. And both times it will give you an LN regression. It will give you an LN equation, okay? So if you haven't done that yet, pause me before I show the answer. And the answer would be, you should have gotten -200.0075 plus 28.9326198 times ln x. And it asks for the value of b to the nearest 10th. So this is your b. And then to the nearest 10th then would be 28.9. Okay. All right. Now, again, lots of words. No biggie, Okay, we're just going to read through, try and get an understanding of what's going on here. When objects with different masses are compared without a scale, their masses must be different enough to be noticeable. Okay, I have a Casio and a TI in my hand right now. Okay, their masses to me are not different enough to be noticeable. When I'm holding them both in my hand, I don't really notice a difference. Okay, if I switched, say, this TI with this, we're going to pretend is a really heavy pound of gold, I can notice a difference in their masses now. Okay, so if I was holding something that was 1 pound versus 10 pounds, I would notice that. Okay, but if I was holding something that was 1,000 pounds versus 1,010 pounds, I probably wouldn't notice the difference there. Okay, that's what they're trying to get at here. So that minimum amount of mass difference is called the minimum perceivable difference. For heavier objects, it's larger. Okay, and so bunch of information in this question, but all you're really doing is determining a logarithmic equation. So this is another regression question. You're going to go menu stats. If you're a Casio, you're going to go stat edit. If you're a TI, type that into list 1, type the MPD into list 2, and do the regression. Okay. Again, on a Casio, the regression option you're choosing will say log, and on a TI, the regression option you're choosing will say LNREG. Okay, and then that should give you an A value of negative 28.2 and a B value of 7.2. Okay, when rounded to the nearest tenth. Now, the next question, so I just put up the equation up top there for you, but the next question says, according to the logarithmic regression function, determine the minimal perceivable difference to the nearest gram for an object with a mass of 2100. Okay, so you were given a mass of 2100. Is that 2100 an X value or a Y value? It's an X value, so you're going to go plug that in for X. Okay, and then you can just type that in your calculator. You don't even have to graph anything for this guy. Okay, and so you should end up with 27 grams. The minimal perceivable difference is 27 grams if my mass is 2100 grams. Okay. Okay, awesome. Oh, sorry, didn't mean to do that. Ahmed invests $1,000 for 4 years into an account that pays 3% per annum. Now, lots of kids get confused about this, and this is the way it will be written. It's percent per annum. Annum means year, so it means 3% every year, okay? Compounded annually. Which of the following functions models the value V of Ahmed's investment in 4 years' time? Okay, well, investments grow exponentially. So right away, I would want you pretty darn comfortable to say C and D are not an option, okay? So now I have to look at my rate of growth. Which one of these guys is actually going to grow by 3%? Remember, it's this guy that will grow by 3% because it's greater than 1. This guy, actually, if you follow this B minus 1 concept, that investment is shrinking by 97% every year. Okay, that is not an investment you want to invest in. Okay, so the answer would be then A. Okay. All right. Since 2007, Alberta has had an average annual population growth of 2.1% per annum. The population of Alberta in 2007 was approximately 3,490,000. Assuming the average annual population growth rate remains constant, which of the following equations could be used to determine the number of years N required for the population to increase to 6 million? Okay, so couple of things going on. Number one, here is our growth rate. Okay, so we need to think of our rate of growth as the decimal, and because it's growing, we need to add 1 to it. So I would want you to rule out A right away from that conversation because there's not a 1 there. And I'd want you to rule out C right away from that conversation because there's not a 1 on the growth rate. Okay. Now I have to think, okay, the 3 million and the 6 million are in two different spots. So I have to know which parameter gives me my starting population and which parameter gives me my ending population. A is your starting population, Y is your ending population. So I need a starting population of 3 million and an ending population of 6 million. So that's going to give me an answer of D. Okay. All right, and that's it for this section, okay? So hopefully this is feeling okay. In the next section, we'll kind of dive more into log laws and see what we can do with that, okay? I'll see you there. Take care.